So again, half-life has to do with something that's being lost. So that's automatically an exponential decay problem just from that alone. So the half-life of caffeine, let's say in a person's bloodstream, is about 6 hours. So if a person's bloodstream contains 80 milligrams of caffeine initially, how much of it will be there after 14 hours of fast? Okay, so we have to solve this problem. So equation is still the same. N of t is equal to n naught e to the kt. Okay, so we don't even know what k is yet. So we're looking at the decay factor. We need to figure that out. So k is not known to us, but we know it's going to be negative because it's a decay. So when I solve it, I'm going to get some negative answer for that. All right, so you have 80 milligrams initially. So the n naught value is going to be 80. That's the initial amount. So it says the half-life is 6 hours. So the t half is 6 hours. Now, again, that's the amount of time it takes for the initial amount to be reduced down to half of its amount, right? So if I have 80 milligrams in the beginning, so this is at t equals 0 hours. After 6 hours, I'm only going to have half of it left. So I'm only going to have 40 milligrams left after 6 hours of fast. So therefore, that's like an amount. So this means that this is like my n of 6 is going to be 40. So I need to put in 40 on this side of the equation. That's my n of t, or n of 6. The initial amount is still 80. E to the kt. So t is t half in this case, right? It's still a time. So I'm going to put in 6 for that into the equation. We need to figure out what k is. We don't know what that is yet. The decay factor has to be solved. So the equation becomes 40 equals 80 e to the 6k. So we saw exponential equations the other day. So these are just applications of that. So I'm going to divide both sides by 80. So 40 out of 80 is a half. That cancels out. So I just get e to the 6k left over on the right. So what do I do now? Remember that we have the natural logarithm of x is log base e of x. I'm going to ln both sides, okay? So you know that ln and e are going to cancel out. We saw that the other day. So if I raise both sides to e, that cancels out. So all I get is the power left here. So I get ln of a half equals 6k on the right. Okay, so what about this property of logarithms? So if I have the ln of a over b, it's a quotient. Well, I can write it as ln of a minus b, ln of the numerator minus ln of the denominator. So I can actually do that with this. And also, if I take the ln of 1, it's actually equal to 0 in mathematics as well. So this is going to help us simplify the equation a little bit. So this would mean that I get ln of 1 minus ln of 2, right? Ln of A over B. This is like A and this is like B. Equals to the right side, 6k. It's still there. But we said ln of 1 is 0. So this is going to be 0 minus ln of 2 equals 6k. So 0 minus ln of 2 is negative ln of 2 equals 6k. So I divide by 6 on both sides, I get k is equal to negative ln of 2 over 6 is my decay constant. Any questions? And of course, mathematically on the calculator, it's approximately negative 0.1155. So 4 decimal places. So again, we said that it was going to be negative because, again, we're dealing with exponential decay. So this had to be negative. And our math confirms that it's negative. So we have an equation, right? N of t equals n naught e to the kt is a general form. The person had 80 milligrams in their body, right, from the beginning. So n naught is 80, and we just found k a minute ago. So k is approximately negative 0.1155 from our math. So if I want to model the situation, all I have to do is replace n naught in k in the equation. Then I have a general form of this. So I'm going to get n of t is equal to n naught, which is 80, e to the kt, which is a negative 0.1155t. So this is like my exponential model for this problem. So now I can actually answer the question. So the question says, how much will be in the person's, how much caffeine is going to be left after 14 hours is what we want to answer, right? How much of the caffeine will be there? So we can answer it by plugging in 14, right? So we're looking for n of 14 hours. So wherever I see a t, I need to plug in 14. So I got to put in 14 here, and then I have to do all the math. And I told you that E is approximately 2.71828 from this page here. So E is approximately 2.71828. You could always use that as an approximate value. You have to use your order of operations to do this problem. Just like any math requires order of operation. So if I multiply negative 0.155 by 14, I get negative 1.1617, or actually negative 1.617 if I multiply those together. So I have to do the exponent before the multiplication. That's PEMDAS, so we do this one first. And then we can multiply last. So this is where you take out your scientific calculator and let that do most of the work. So if I raise it to that power, I get 0.198493503 on my calculator. So if I do that exponent. So I did the exponent. Now we can finally multiply by 80. So we get approximately 15.88, which is about 16 milligrams after 14 hours of fast. So about 16 milligrams. So what happened? We started out with 80 milligrams right away. That was the initial amount. After 6 hours, we only had 40, right? So 40 is like after 6 hours. After 14 hours, only, 16 milligrams left. That's not even half of 40. So at 0, I have 80 milligrams. The half-life tells me 40, and then 16 after 14 hours have passed. So this looks almost like the curve that I drew over here. Has the same shape. So it's decreasing, gradually decreasing until it gets to the t-axis as time goes on. Okay? So it's an example of exponential decay, basically. So it's not the only situation where we get exponential decay. It could come up in other fields too. So again, with population decline, if there's a lot of crime in a city, let's say Detroit. Detroit's pretty bad. People were leaving for a period of time because it's not safe. So you might have had like an initial amount of people, like maybe 1,000 people, let's say, or 2 million people. And then after 5 years, there might have only been, 900,000. So that's an example of decay as well. If it has that model, we can form an exponential model for stuff like that. So let's look at another example.